Hello, welcome back. Today we're going to add recurrence into memorizing transformers. So we've built out pretty much everything we need to build out for memorizing transformers. We made an attention block and we made an attention block with KNN augmented memory. And the last piece that we need to put into these blocks is recurrence. And this is recurrence via transformer XL. So this is a very specific kind of recurrence, but before we get into the details of this paper, I'll just briefly cover what recurrence is in case you're not familiar. So before transformers became kind of the dominant paradigm of language modeling and NLP, recurrent neural networks, RNNs, were a very, very popular choice for language modeling. So what is the basic idea here? There were many, many variations, but the kind of defining characteristic can be summed up in this graph. So this is a very stripped down abstract computational graph, but it does get to the heart of what's going on. So let's say we are language modeling, meaning we have a sequence of letters, and at each step we'd like to correctly predict the next letter. This is our input letter. We want this to be the correct output letter, and this middle node in the graph is basically just some kind of computation. It can be as simple or as complex as you want. And there were very many variations for what kind of computation goes on in this middle state. But the defining characteristic here is that in addition to this computation taking an input letter and producing an output letter, there's a second input. So one input is the input letter. The second input is the output of the computation at the previous time step. So we can unfold this graph, as it's called, and you just get a laid out explicit version of what's going on at each time step. So each time step is a successive letter, and each time our computation is going to take the current letter. It's trying to predict the output letter, so taking time step t letter, trying to predict xt plus 1, and the other piece of input that it takes is the output of the computation of the previous step. So at each step, the model asks, what is my current input, and what was the result of the computation of the previous input? And I'll use both of those pieces of information to predict the correct output. So it's recurrent because you have to do this for each time step. So to predict the nth letter, you have to predict the n minus 1 letter. So you have to go back, and this must follow kind of in sequence. So why don't we use RNNs anymore? Well, transformers came around and they addressed two of the main problems that RNNs had. So what are the two problems? The first is that as you move forward in time, the information from far back at previous time steps, so if you're up here, if you want to go back here, that information has been attenuated. So if you're at token 100 and you want information from token 1, it's really been attenuated, and you've lost a lot of the information that you had at the beginning of the sequence. So this is a video by Michael Fee, but it has a great illustration of this, where as we go through forward in time and we process new words, the fraction that a future word sees of a very distant token is very small. So there's a built-in locality bias. You're paying more attention to local words. This can be good. It's what we do when we add positional encoding into our transformer architecture, but it can be bad if everything that isn't recent decays like crazy and you struggle to keep the information propagating through. So that's one problem. The second is that the architecture isn't parallelizable. So it's recurrent, meaning that to compute this, we have to compute this. To compute this, we have to compute this. So you have to go through one at a time, and you can't compute anything until you've waited and returned the results of the previous computation. So these are the main problems, and transformers kind of address these in a nice way. So on the first point, every token attends to every other token directly. When you're creating the similarity attention scores with the query and key matrix, it doesn't matter where in the sequence a token is, it gets to directly interact with every other token in the sequence. So there's global pairwise dependency. The trade-off is that there's no positional encoding, as we've seen, but we've added that in different ways. But the real big reason that we don't use these as much is that we couldn't efficiently parallelize them on modern hardware, so specifically GPUs. So if you have one sequence of 512 tokens, in a transformer, you get to instantly create 512 training examples. You don't have to wait on the results of one to process the next. You can just leverage GPUs, create a bunch of matmuls, split them up across GPUs, and scale. So this was super powerful. All right, so what is Transformer XL exactly? There's not many details in the paper itself. It just says we use Transformer XL recurrence. So we have to head into the paper to see. And you can read about this. The main section is 3.2, and this basically explains everything that goes on. But I'll give you a very high-level overview and a kind of picture intuition, a pseudocode intuition, and then of course we'll actually code this all out. So what's the main idea? Is we're introducing a kind of efficient, sort of a hacky version of recurrence that lets us see previous segments of a long document. And this isn't overly expensive to compute. So if you remember the recurrence relation, when it applies at each time step, if each time step, say, is a different letter or token, each one has to wait on the previous computation. So the recurrence here is not between examples or words or tokens, but between segments of the document. And we already know from the way this model is set up that we're going to feed in a batch of segments of some long document. So we'll feed the first segment in, and then the second segment. So the recurrence is between passes of the model over an entire batch of data, rather than between specific examples. So that's why it's much less expensive to run, and kind of why it's a hacked version of recurrence. But basically this allows one section to see previous sections. Let's look a little bit at the paper, and the main, if it lets me zoom in here, the main idea here is, you can read the notation, but we concatenate the, what will we call this? The two hidden sequence states. So from t, we concatenate that with t plus 1, meaning the previous, in this case, these will be key values. Stop gradient just means the gradients don't flow through this. This is just cached key values. We concatenate them to the current input, and then we perform attention as usual. So this is all just saying we perform attention as usual once we've updated our key values to basically concatenate with the key values of the previous segment, so the previous text segment in our long document. And this is the only picture, so you have to stare at this a little while and make sense of what's going on. But to give you an example, all right, our first text segment goes in, and this is kind of the iteration of how it goes through. First text segment goes in, we compute at each layer the KV projections, and we store these in a list. And then that runs through the model, and then a new second segment is fed in through the model. And so we retrieve those old KVs, and we prepend them to the current KVs, and we run that through, and we perform attention as usual. So the only real caveat here, or maybe unexpected thing, is that at each time step, we only look at the previous KV values. So we don't say we're on segment 6, we only concatenate the KV values from segment 5. We don't look at 4 or 3 or 2 or 1. So at each state, you only ever concatenate 2 at a time. But the idea is that because if you're at segment 6, you're concatenating segment 5, certain layers of segment 5 have actually seen concatenations from segment 4 and 3 and 2 and 1, and so on. So this creates a kind of recurrence through past segments, but how much of the past we see depends on both the sequence length and the height of our network, so how many layers we have. And this is basically what the triangle is demonstrating. So if we are, and I believe in this diagram, we're going 4 nodes at a time, so x1 through x4, x5 through 8, and then 9 through 12. So if we're here, that is the input, and then if we're here, we can only see these previous 4. because we're only at the second layer. We don't actually, there's no lines connecting our inputs here back to there. When we get up here to this layer, there are in fact dependencies that have seen something at time step 3. So basically, if you're very high up in the network and you're further along in segments, so you're on the 10th segment and you're on the 10th layer, then you can actually see back quite a ways. So this is just the explanation of how recurrence is flowing through the network. And that is your picture explanation, and then I've laid out kind of a pseudocode version that we'll just model our actual code on. So step by step, the first segment goes in, compute the current KV projections, and we perform attention as usual, so nothing happens here. This is regular self-attention. For the second segment, we concatenate the old KV projections with the current KV projections, and we perform attention. And we do this with the third and the fourth segment, and each step we're looking back one segment. And so, for example, the KV values for segment 3 will basically just be this concatenation of, for each of these layers, segment 3 layer 1 concatenated with segment 2 layer 1, and then for the second layer, segment 2 layer 2, segment 3 layer 2, and so on. So we're just creating these values, caching them, and then pulling them in and performing attention. When that's done, we discard them and we repeat the step for the next segment. Okay, so let's get started and let's actually build out an attention layer. So I'm going to follow basically the process we used for building all of the other sets of attention, but I'll move through a lot of the basics that we've already covered more quickly, and I'll just highlight the differences that we're going to change here when we're adding in the recurrence. After that, we'll build out the full classes for both regular attention and our KNN augmented attention that will also have recurrence added in. So we're going to build out both of these classes. All right, so I've already installed kind of the main libraries here, and we're going to do what we did in previous videos where we are constructing attention. We're going to create some fake data, and we're going to pay close attention to shape and what's happening, just to make sure that we understand how the data moves through our model. So I've got some fake parameters here that will just help us keep track of our fake input data that goes through. So 16 batches of 512 length sequences, and I've arbitrarily chosen the embedding dimension as 13, just so we can keep it separate from head dimension and keep it distinct. Once again, we initialize some query key value output matrices, or rather linear layers, and we'll feed our data through this. Okay, so now we've got our fake query projection, key projection, value projection. Here's the new step. We're going to create some fake XL transformer style recurrence. So we're just dealing with one transformer block, one layer. And at this stage, we would pull in the old recurrence and we would concatenate it to our keys and values. So I've got some fake XL memories. So this is from the previous text segment we're pretending, and this is 16 batches, 512 sequence. 80 is number of heads times head dimension. So 80 is just the dimension we're working with, and there's 2 because we've bound together the key and the values. So that's just the interface of how we're going to move this around. We could have them separate and pass them both in, but it's a little easier to pass them in as one variable. So let's first split these out. And we're going to split these out on dimension -2, which is this one. So this will just unpack these and get the correct data that we want. So each of these is now in the correct format. And here's where we update our keys and values. So we have XL recurrence keys, XL recurrence values, and we're going to update our keys. to say cat is the concatenate function. XL keys comes first. Remember, we're prepending these. And then keys come second. And this is along the sequence length dimension. We'll do the same with values. Okay, so now our keys and values, instead of being 512 tokens long, these are 1024 long. And now we're just going to perform attention as usual. You might think that that will go wrong somewhere because we've changed one of the sizes of the dimension, but it does work out, and that's why we're splitting this out into individual steps so that we can actually see and verify, oh, this does work, this does make sense. Okay, we've concatenated these. These have the same shape as keys and values, are both 1024 long. And let's recall that our query is 512 long in this dimension. And now we're going to perform the attention scores using InSum that we introduced in the last video. And let's take a look at what happens here. So one matrix, or rather one tensor that is 512 by 10, this is 1024 by 10. What we want is attention scores that are 512 by 1024. So this means that for each of the 512 in our current sequence, which is the queries, we're attending both to the current key values and the recurrent key values. So current and recurrent. Sorry, that's a little unclear. But basically, this allows the queries to attend to the previous segment at this specific layer. And that's where the ability to look backwards is coming in. So we're able to look backwards at those projections from the previous text segment, and we have attention scores that can be applied to those. And so when we multiply this by the values, we'll actually just be basically saying how significant were any tokens in the previous segment, and the values, we can pull that out and we can incorporate that into our final attention score. But before we get to the values, we have to mask this out because this is causal language modeling. So if you remember, we've already kind of built this out. It just looks a little different here than it did for regular self-attention. So regular self-attention, remember, this will be the first token, and we don't want to attend to any future tokens because this is the first one and we don't want to look forward. We only want to look backwards. Similarly for here, we want to predict the third token, but we don't want to see it. So we mask it out. And once again, we're applying a very large negative number here so that our softmax function, when we apply it through softmax, will turn these into 0. So the probability distribution will only be over past tokens. Therefore, our attention scores will only look at previous tokens. In Transformer XL, the same thing applies, except that we get to see all of the previous tokens of the previous segment. So at each step, the probability distribution is spread over not just the current tokens, it's spread over the previous tokens. So we're just applying it this way, and we should get the shape of this just so we have it. We'll call it ij. We want the last two. Okay. You remember that for our mask we used an upper triangle function. And one of the parameters of this upper triangle function just tells you, so you've got this matrix, where do you want me to start masking things out? And so we can actually just apply the correct value and it will mask it out perfectly for us. So it's actually, this is a very simple thing to implement because we've already built it out and we just change one of the values here. Or rather, the value is changed for us, but we've already built it out to generalize. So we have that function here. Our mask is a series of ones, and we're doing triangle upper it's j minus I plus 1. The plus 1 is just an indexing, so we're on the correct diagonal. But j is now 1024 and I is 512. So this will create this style of mask. Whereas when I and j are the same, j minus I is nothing, so this is always 1. So this is going to work correctly for us. And now we're going to fill the mask with negative infinity. So I've put negative 1000 here, and that's just so we can read it legibly. And we're going to apply this to the QK attention scores. And now when we apply softmax, those very, very negative numbers under softmax turn into 0 because we exponentiate them. And then once again, we can just check that this is working correctly. This is great. So the rows are adding up to 1, and that's what we want. Okay, so that's really the hardest part, and the rest just looks like regular self-attention. And then, of course, there's one bit at the end where we have to remember to pull out the XL memories and store them so that the next segment we can actually pass them forward. But this is kind of the hardest, meatiest part done. So really, all we would do is use einsum to create QKV, that is the QK attention scores with the mask applied. We now apply it to the values, and we'll see that the shape comes out correctly. So QK was 512 by 1024, and the values, all of these 1024 sequence lengths get applied here. And so when we compute QKV, we can just do that here. Great, now we have exactly what we wanted, which is we have this output that is being passed forward that is of 10 dimensions. So remember, this isn't quite in the right shape, and I'm sure you're very tired of dealing with shapes and reassembling heads and splitting them out, but I'll just walk through the last few steps that we've seen a few times before, just this good practice. So we fold the heads back in and we rearrange this. So once again, we have what we're looking for, 16 batches of 512 length sequences, and each of these is 80 dimensions. And now we had our output matrix already defined. Yes, 80 by 13, so 13 was our arbitrary embedding dimension. And when we compute our output, which we'll call out, it's output matrix times QKV. And there we go. So this gets passed on to the next block, and the only step that we've missed here, which we'll include when we actually build out the class, is to make sure that we hold on to the KV values for our current KV value projections. We hold on to those, and we pass them forward so that for the next segment, the next text segment, they will go in here, and they won't be fake. They'll be passed forward. So there we go. We've built it out, and now I'll basically tidy this up and turn it into a class, and we'll look at that. All right, so I've copied over our regular self-attention that we've created. So I've just directly copy-pasted this as we made it in the last video. So this is normal attention, and we're going to turn it into XL attention. So all I've changed is the class name. So what do we need to do? The first thing we need to do is somehow pass in the XL memory. So we can just do that in the forward pass, like that. And we'll actually leave it as none as a default. And this is mostly to handle the first segment that is passed through, which will by definition have no XL memory that can be passed to it, because it's the first segment, so there's no recurrence relation with a previous segment. Nothing has come before it. Okay, And now here we get the keys and values. So remember, we need to, if this exists, if this is not none, we need to append these values to our current key values. If XL memory is not none, and you can kind of build this logic however you like, but this is a very explicit way, we'll say that our XL memory, like it was in the example we just saw, we'll say it's bound, so the keys and values are bound together, and we just want to split them out. So the XL memory, unbind it along dimension -2. And then, once again, we're just going to concatenate the keys and the values. So the recurrence memory comes first, then the regulars, rather the recurrent, and then the current comes. Great. So otherwise, nothing happens. The keys and the values stay the same. So if this is the first segment, the keys and the values stay the same, and we're just performing regular self-attention. What else? Okay, this is the only part we haven't covered, and this is, at the very end, we need to make sure that we pass on the keys and values so that the next segment can use the recurrence key value projections. So once again, if XL memory is not none, or rather, we've gone back and forth rearranging how the heads are folded into the head dimension and how this is arranged. We're going to redo it one more time, and this is not an efficient way to do it, but it is very explicit, and so it's a good way to write it for now. We're going to add the XL memories, or rather, return XL memories. So we've just gone to the trouble of rearranging the keys and values, and now we're rearranging them again, even though we had them up here. And we're stacking these. So this is, we're binding, we're stacking these, and when we retrieve them from a previous time step, we unbind them. This is just the convention we're going to use because it's easy. So if XL memory is not none, this means if we're in the middle or end segment of a document, so if we're somewhere in the middle or end of the document, then we actually need to make sure that we don't just pass the keys and values forward. We actually have to split these out. So we can do that just by saying, let's add XL sequence length, which I forgot to do up here. And this is just saying, what is the size of keys or values, just so we hold on to that shape so we can use it later. So here we just want to make sure that we've got the recurrent KVs and the current KVs, and we just want to split them in half. So these are XL memories, and this is the current input. And the KV that we want to add is just the current input. Remember, at each time step we discard these. Once we've concatenated them, we don't use them anymore. So we're getting rid of these. We're very explicitly writing that we're going to hold on to the current input, and this will be the KV to add to the XL memory that gets passed on to the next segment. Okay, and if this is the first segment of a document, then KV to add XL is just the KV memories. We didn't have to modify them, we don't have to split them out, because there's been no recurrence added in. So these are already the correct output we want to give. So the only other thing is we're going to return KV to add XL. So we're returning the current KV projections that we've created during this pass. And inside of the wider model, we're going to hold on to them, store them, so that for the next pass, we can pass them through. All right, we're in the home stretch. So the last thing we need to do is to take our KNN attention class and add the recurrence. And here there's really nothing more complicated than we just blend these. So we'll take this KNN class, which is copy-pasted from the previous video. It's exactly what we made. And just as we did above, we'll just add in the XL recurrence in the appropriate places. So pretty straightforward, even though it ends up being a very long class. Conceptually, we're just putting these two together. So KNN is already in here. We just need to add the XL memory. And then we're adding this block in after we compute the current key values. If the XL memory is not none, then we prepend the recurrent memory to the key values, just as we did above. And the last step is then to fix the output, just like we did. So we're taking do it here if we like. Once again, and it's even worse in this class, we're rearranging our keys and values again and again. But for us, this is very simple and legible to read. At least we know what's going on. And here we're going to, if XL memory is not none, then we split out the KV memories just as we did above. Otherwise, if we're on the first segment, the KV memories don't need to be touched. They're good as is. Here we will add, I don't see where we're adding the KNN. I guess we forgot to add that in, but it's one line. So our current key values will be added both to the KNN memory and they'll be passed on as the recurrence relation for the next segment. So that's what current KV is, and we've successfully passed it on to both the KNN, and we're going to store this in the outer model and give it to the next pass. So at this point, we've built KNN, augmented attention, with XL recurrence wrapped in. And this is really the last main big component that we have to build for memorizing transformers. So the rest of the work is filling in a couple things, like we need to go ahead and add in relative positions, but it's really as simple as one or two lines just like this. There are things like dropout. We need the appropriate scaling, but these are all kind of minor details. We'll also have to wrap these attention blocks in feed-forward layers, create residuals. Now that I'm saying it, there's actually a lot of things, but they're all fairly straightforward. And when we're wrapping these things all together, that's kind of the fun, simple part. We've built the really hard, kind of complicated machinery here. And the rest is just tying these things together. So let's do that. Let's tie it together, run it end to end, and start training our model.